Hello all, let us start concrete mix design in this class. There are various types of concrete mix design adopted anywhere in construction industry. In that arbitrary method, ASTM method, ACA method, then concrete mix design by IS 10262. Now we are going to discuss about IS 10262 2009 method. Let us see what and all aspects we need to remember and how the mix should be designed. In part A data, you need to note down the data which are required to design the concrete mix, such as uh, the type of cement which you are using. In that, uh, in this number, we have taken OPC 43 grade concrete, OPC 43 grade cement. We know that 43 is a 43 MPa strength of cement, ordinary Portland cement. Fly ash conforming to IS 3812. This is IS code which gives the specification for this fly ash. Then maximum nominal size of aggregate 20 mm. 320 minimum cement to be used in this particular mix design is 320 kg. So maximum water cement ratio 0.45. Workability required in this concrete mix design is 100 mm. Then severe exposure condition to be adopted for RCC. Then concrete is to be placed in the form of pumping. So these are the data required to design the amount of aggregate required, that is coarse aggregate required. Then degree of supervision is good. Crushed angular aggregate is used, type of aggregate. Then maximum cement content 450 kg. Chemical admixture is super plasticizer. Test data for the material. Once the material arrives to you, you have to test the material and get the data such as specific gravity of cement, fine aggregate, coarse aggregate. So it is noted down here. Then specific gravity of fly ash is also required, that is 2.2. Then water absorption test needs to be conducted for both. It is coarse aggregate, it is 0.5%, and for fine aggregate it is uh, nil. So it is not always nil. It may be of some of the percent for a given aggregate. Now it is nil. Then free moisture or free surface moisture is to be taken as coarse aggregate. It is nil because it is stored under the silo, it seems inline silo. And for fine aggregate it is 1.5% free moisture. Grade of coarse aggregate conforming to table number 2 of IS 383. This IS 383 recently revised in 2016, introducing uh, crushed rock fines. Earlier it was not there, but now they have introduced that in 2006. Grade of fine aggregate conforming to grading zone of 1, table number 4 of IS 383. So let us step by step procedure to design the concrete mix. First, let us see the how to calculate the target mean strength. See, this target mean strength is very important as per as mixed design concern, because these target strengths needs to be adopted or achieved at the laboratory conditions. Once this target mean strength achieved in laboratory conditions, then you can supply the concrete to the site. Otherwise, it will be very difficult to get the strength. So how this target strength is calculated? See, the M20 grade of or M40 grade of concrete in this mixed design they have given. Yeah, to design M40 grade, FCK, that is characteristic compressive strength, will be 40 Newton per mm square or 40 MPa or 40 kilonewton per meter square. All are same. You have to note down the FCK value. After that, FCK dash equal to FCK plus 1.65 into S. So S is a standard deviation. This standard deviation should be taken from minimum 30 samples from the site. Once you get the 30 samples, you have to calculate the standard deviation, though it can be initially assumed as per the table number 6.4 of IS 10262. You can assume it and put it. For grades of M40 or above M25, it is taken to be 5. So 40 plus 1.65 into 5, you will get 48 MPa or 48 Newton per mm square. This this strength needs to be achieved at 28 days in the laboratory conditions. This is a minimum required strength to be achieved at the laboratory conditions. Step 2, water cement ratio from table number 5 of IS 456 2000 for the given exposure condition. In this problem it is a severe given exposure condition. You have to choose least up among the two conditions. One condition is maximum water cement ratio specified in IS 456 under severe condition for RCC, that is 0.45, and based on the experience of the mix designer, the water cement ratio needs to be taken somewhere near 0.4. So how it comes experience, actually what happens, the designer will do n number of mix designs, and he goes for a trial. He do n number of trials using pan mixer or in drum mixer, and based on his experience he can choose the water cement ratio required for his mix. Based on those two, you have to adopt the smaller value. So smaller value is zero point 0.4. So zero point 0.4 is a water cement ratio we need to adopt. Basically it comes like, for M40 it comes, sorry, M20 it comes somewhere near 0.54 or 0.55, and for M25 it will come now somewhere near 0.55, sorry, zero point 0.5 or 0.4. You can take 0.49, you can take. And for M30, 0.45 is the experience water cement ratio. So basically the thumb rule is you have to reduce whatever given in maximum water cement ratio as per IS 456 and adopt the water cement ratio least of these two. So this is how you need to adopt the water cement ratio. Next, step 3 is water content selection. In this water content selection, IS 10262-2009 plays an important role. Maximum nominal size of the aggregate we have noted down in the part A, that is 20 mm, and maximum water content as per the table number 6.6 corresponding to 20 mm size aggregate, it is 186 liters for 50 mm slump. For any 50 mm slump you can use 186 liters. For the given aggregate nominal size is 20 mm. Maximum nominal size of aggregate is 20 mm. If 50 mm slump is required for the 20 mm aggregate, water content comes to 186. But in this case, we need a slump of 100 mm. It means that for every 25 mm slump increment, you need to increase 3% of the water. So how many 3% of the water we need to increase here? Up to 50, we have 186 liters. After 50 there are 225 mm, that is 25 plus 25 100 mm, total 50 plus 25 plus 25, 50 plus 25 plus one more 25. It means that for 50 we have 186 liters of water, plus for 25% 25 mm slump we need to increase this 186 at a rate of 3%. So how many 3% I have to increase? 2 times 3%. It means 6% I have to increase the amount of water required for the slump of 100 mm. If it comes to 125, you have to increase one more 3%. That is, it comes to 9% again. So what you are going to do is basically 186 plus 6 divided by 100 into 186. You will get 197 liters of water to achieve a slump of or workability of 100 mm. So as super plasticizer is used in this problem, so that is why the super plasticizer can reduce a slump of up to 30%. Sorry, super plasticizer can reduce water content up to 30%. Basically BASF chemicals, post rock and many other chemical construction chemical manufacturers, they are producing super plasticizer and all. In that there are two types, naphtha based and PC based. Super plasticizer generally comes in PC based, polycarboxylate based what admixture, which can reduce up to 30% of the water. Let us assume it can reduce only 25%. If the amount of water which is utilized for the mix design as per the calculation for 100 mm slump is now 197 liters, but as we are using super plasticizer, you can reduce the water content by 25%. If I reduce 25% of water, how much water is left out? Only 75%. That is why I have taken here 197 into 0.75, or you can write like this also, 197 into 75 divided by 100. That is also same, that is 148 liters of water you need to utilize for the mix. This is the free water you need to utilize. If in case the uh, plasticizer is used, so that is naphtha based admixture is used, then you can reduce it up to 10 to 15% of water, or you can sometimes even 20% also. You can reduce it based on the trials, based on the experience. This reduction will be adopted, and as well as the humidity consideration, as well as the locality and all. If you design the mix in Bombay, it the admixture usage will be very high. That is in turn the reduction water will be less. Whereas if you utilize in Bangalore climate, you can reduce the admixture content in a nominal amount, whereas the reduction of water content can be done at a maximum extent. Let Step number 4, binder calculation. Cement plus fly ash content needs to be calculated. In this problem, we have mentioned the fly ash properties, so we are going to use fly ash in the uh, binder, that is double blend. So water cement ratio, which is calculated in the previous step, is 0.4. Water content which is used is 148 liters. Cement equal to 148 divided by 0.4, that is water cement ratio that we have already known. Water cement ratio equal to water by cement. So if I want cement to be calculated, so I'll take a cross multiplication and I'll get the cement. This is the amount of cement we are going to use. But as per the IS 456/2000, table number 5, minimum cement content for the severe exposure is mentioned. That is to be 320 kg per meter cube. That is a minimum cement you need to use. Whereas the arrived mix cement is more than the minimum requirement, hence it is safe. So 10% increase you need to do, 10 to 15% increment in the total binder content you need to do if you are using any other mineral admixtures. That is 370 1.10 is because increment of 10% of the total binder, it comes to 470. It is just like 370 plus 37. 37 is a 370 into 10 divided by 100. So you will get this much of total binder content. In this total binder content, uh, again you have to proportionate for fly ash and cement, that will decide. Before that, we will see the revised water cement ratio. Water content is 148 and the water cement ratio is 148 divided by 407.364 is a revised water cement ratio. Fly ash, we can use up to 30%. No code in the industry specifies us to limit the fly ash content. No code limits the amount of fly ash to be used in the concrete mix. They can suggest the limiting of fly ash for the cement but not for the concrete. So fly ash content to be used is up to 30%. It suggests 35% for the PPC cement, but it doesn't mean that we need to limit for 35% in for the concrete. Concrete you can go up to even 50% also. So that is HVFAC we have already discussed. HVFAC is nothing but high volume fly ash mixes. There the increment is up to 50%. So in this mix we will assume that fly ash content to be taken as 30%. So 30% of 407 becomes 122 kgs. Cement content is 107 minus 122, that is again 70%, 285 kg. So cement content saved due to this usage of fly ash is 370 minus 285. You saved 85 kg of per meter cube of cement, whereas fly ash is much cheaper than the cement, and fly ash is just a waste product from the power plants. Let us see next step. For 5, determination of coarse aggregate and fine aggregate content, or percentage of coarse aggregate and fine aggregate. From the table number 6.8, maximum nominal size of aggregate is 20 mm. Coarse aggregate which is used equal to 0.6 plus 0.02, because as per the table number 6.8 of IS 10262, for a given 20 nominal size of aggregate and for water cement ratio 0.5, it is 0.6. But in this current case, we are using water cement ratio of 0.4, is a 0.4 is a arrived water cement ratio. For it means it is lesser by 0.1 from the 0.5. It is lesser by 0.10. So we need to increase the coarse aggregate content at the rate of 0.02. That is, as water cement ratio is reduced by 0.10, so increase coarse aggregate by 0.02. It means for every 0.05 reduction in the water cement ratio, you need to increase the coarse aggregate by 0.01. So that is why we have done. There are 2.05, 2 times reduction of water cement ratio, that is 0.5, 0.05, 0.05. That increases the content of coarse aggregate to an extent of 0.02. Hence, the arrived coarse aggregate content is 0.65. It has increased to 0.62, sorry, 0.62 increment. So since we are going to place the concrete by a mechanism called pumping, for pumpable concrete, you need to reduce the coarse aggregate content and increase the fines. Hence, if the concrete has got good fines, it can be cohesive and it can pump easily. There will be no choking of hose lines, pumping lines. For that, you need to reduce the coarse aggregate by 10%. It means you are indirectly increasing the volume of fine aggregate. That is why 10%, if you use reduce 10%, how much you are going to use? Only 90% of this amount. Reduce volume of coarse aggregate equal to 0.62 into 90, because 0.90, because 10% we are going to reduce. It means you got 0.56 as a volume of coarse aggregate. So 1 minus 0.56 is a volume of fine aggregate. So it means 56% of coarse aggregate you are using, 44% of fine aggregate you are using out of all in aggregates. Let us see the next step. This mechanism you need to understand during the calculation. This is very important. For every decrease in water cement ratio from a benchmark of 0.5, 0.05, that is out of point, if I reduce water cement ratio 0.5 to 0.45, I have to increase coarse aggregate to 0.01. If I reduce to from 0.5 to 0.4, that means I am reducing 2 times 0.05. It means I have to increase 0.1 2 times. Again, it means 0.02. So let us see the next step. Mixed proportion calculation. Volume of concrete is 1 meter cube. Volume of cement equal to mass of cement divided by specific gravity of cement. So mass of cement is calculated as 285 divided by 3.15 is the specific gravity of cement into 1 divided by 1000. You are going to just convert it into meter cube. This is 1 meter cube. This is 0.09 meter cube. Again, mass of fly ash equal to fly ash divided by specific gravity of fly ash divided by 1 divided by 1000, because you are converting into meter cube. So it becomes 0.055. Again, water is 148 divided by 1. Specific gravity of water is 1. 1 divided by 1000. It becomes to 0.148. Then again, volume of chemical admixture is 8.14. Not always it comes 8.14. It can be even reduced based on the trial. You need to arrive for that number. Basically for plasticizer, it may be somewhere near 0.5 to 1%. At the max 0.88% in Bangalore climate, you can use 8.1 I have taken divided by 1.145 is a specific gravity of admixture, chemical admixture, that is super plasticizer. It gives an this much of volume. Addition of all these volumes, absolute volume of all in aggregate is 0.3. So what basically you need to do is 1 minus all these. Let us see step number 7, mass of coarse aggregate and fine aggregate. Absolute volume of all in aggregate needs to be calculated. In this, your one is a absolute volume of concrete, which is used in the concrete, that is 1 cubic meter we are designing. This zero point 0.3 is contributed by your total volume of cement plus fly ash plus cement plus fly ash plus water plus admixture. All these volume together, it comes to 0.3, and zero point 0.7 cubic meter of remaining amount is aggregate, that is fine aggregate and coarse aggregate. So this, if you negate 1 cubic meter out of 1 cubic meter, 30%, that is 0.3 cubic meter is your uh, volumes contributed by other ingredients except coarse aggregate and fine aggregate. That is then the absolute volume of all in aggregate becomes zero point 0.7 cubic meter. So let us see the mass of coarse aggregate, which is equal to V is the absolute volume of your all in aggregate. Volume of coarse aggregate is calculated, that is 0.56. Specific gravity of coarse aggregate is 2.7. Sorry, this is 2.74, which is given in problem, or you need to test it in the laboratory, and which sums up to 1074 kgs per cubic meter. Mass of similarly, mass of coarse fine aggregate needs to be calculated with the same formula. With specific gravity of fine aggregate is 2.74, it comes to 844 kg, it comes to 1074 kgs. These are the mass of coarse aggregate and fine aggregates. Let us see number 8, mix proportions for trial number 1. So in this amount of 40 in the coarse aggregate, out of 10 whatever value we got, 1074, out of 1074 kg, this is a total coarse aggregate content. We can't use everything into coarse aggregate, it becomes a gap graded again. So to make it graded, 40% of the 10 mm aggregate needs to be used, 40% of 1074 kgs, and 60% of 20 mm aggregate is used, 644 kgs. It means that to arrive to a maximum packing density, you need to divide the proportions of 10 mm and 20 mm aggregates. So for 40%, it may be 50-50%, or it may be 55 into 45 also. So in this problem we have arrived 40 is to 60, 40% 10 mm aggregate, 60% 20 mm aggregate for in the amount of 1074, that is coarse aggregate volume. So let us note down the ingredients and quantities in kg per meter cube. Ingredients we have arrived is cement, fly ash, water, fine aggregate, coarse aggregate 10 mm down, coarse aggregate 20 mm down, chemical admixture, and wet density. Addition of all these ingredients, 2481 cubic meter kg per meter cube it will come, and water cement ratio is 0.364. So this is a step number 8. This is a mix, but you can't use all these materials suddenly at the field. So field corrections needs to be done. Let us discuss the field corrections. So, or you can say site corrections. Water absorption and surface moisture will be there at the site. Once you procure the material and lay at your site, or even in your concrete mix plant or batching plants, what will happen, there might be a rainy season, or that maybe summer season, there will be an absorption of moisture, there will be a free moisture if it rains. So let us see in this problem, water absorption is taken as coarse aggregate 0.5%, fine aggregate we have taken nil, free surface moisture coarse aggregate nil, fine aggregate 1.5%. It may be even there for fine aggregate, water absorption will be there for all the sands, coarse aggregate will be there, but let us assume these conditions, these two conditions. In these conditions, what will happen, surface moisture for fine aggregate is 1.5%. so 1.5% of 844, it means 12.66% is is the only water present in 844. So if this 1.5% is a water in the 844 kg, it means that much of amount of 12.66 kg of you know water is contributed by the your fine aggregate. That is why you need to increase that amount of 12.66 kg. That is why what will happen in 844 kg plus 12.66, that is equal to 856.66 kg per cubic meter. That much of fine aggregate will be increased because of presence of moisture. So what will happen? There will be water in the 844 kg. How much water will be there? 12.66. If 12.66 water is there, if I add only 844 kg, what will happen? That much of amount of fine aggregate will go less. It becomes somewhere near 811 kg, something like that, to 822 or 821 kg. If I reduced 822 kg, then the mix will be less coarser, sorry, less cohesive. That is why, to avoid that condition, you need to increase that much of amount of fine aggregate, this much of amount of fine aggregate, and reduce that much of amount of water in your total mixing water. So water absorption of the coarse aggregate, absorption means that much of amount that coarse aggregate needs to become SSD condition, that is saturated surface dry condition. So basically the concrete mix design is done assuming that aggregates are in SSD condition, saturated surface dry condition. So 0.5% of the 1074, that is 5.37 kg, that much of water it needs, which needs coarse aggregate needs to become SSD condition. That is why mass of the coarse aggregate in field is 1074 minus this much. So there are 1074 kg of dry aggregate with your stock, but it needs 5 kg of water to become SSD condition. So that is why what we are doing, so we are reducing that much of coarse aggregate. It becomes 1068.63 kg per meter cube. Then what will happen? That's minus 5.7537 kg needs to be added. That much of amount of water needs to be added to the coarse aggregate to make it SSD condition. Whereas in fine aggregate, what is happening? 12 kg of water is extra in the fine aggregate. That excess water and this required water needs to be negated. So what will we get? Therefore 12.66 minus 5.37, you got 7.29 extra water contributed in this quantity of mixes. That is why it should be deducted in the free water, which is calculated as per the codal provisions. So 148 liters of water minus 7.29 kg of water, which is contributed by your fly ash, sorry, your fine aggregate and coarse aggregate, that is negated, and you got the final water at site is 140.71 kg. Finally, the baseline is if the aggregate is too wet and it needs to be in SSD condition. How, when it will needs to be SSD condition? If you measure the aggregate, uh, you know, water content, then if suppose say certain aggregate comes 10% of moisture and its absorption capacity is 4%, and imagine how much water you need to reduce. Only 6%, because 4% is already its absorption and 6% is excess water. So that excess water needs to be negated in your free water, and that amount of 6% of aggregate increased because of its wetness. So the step number 10 is mix proportions by mass. So cement plus fly ash equal to 470. Water content is 140.71 at the field. Fine aggregate is 856.66 kg. Coarse aggregate is 1068.63. It can be even, rounded up to the next higher value. Water rounded up to the lower value. So the final proportions of the concrete mix at the field is cement 285. Cement fly ash will not be changed, that is 285 and 122. Water will be changed, 140.71. Fine aggregate 856, coarse aggregate 427, 642, and chemical admixture 8.14. Wet density is again the same thing, and water cement ratio revised 0.36. The basic funda of this is you need to make certain aggregate to the SSD condition. You have to make the field correction. That is why in IS 10262 the tagline of note is given: aggregates are assumed to be in SSD condition, the necessary field corrections needs to be done. Thank you very much for watching this video. Thank you.